So this section is on capacitors and resistors. We're gonna look at what happens when you're using capacitors in circuits with resistors. They have to charge up and discharge, and so the simplest example we get is when we kind of start with a voltage source here, and then we've got that to a capacitor, and then we've got a resistor over here, right? And so there's my capacitor, there's my resistor, and then I've got a switch. So I can charge this guy up like that by throwing the switch this way, and that gives me plus charges here and minus charges here, and I can say that Q naught is equal to C times V. In other words, when the capacitor is charged up, before I start to discharge it, I'm going to say it has a charge Q naught on it. Once I start discharging it, now once it's all charged up, then it's got Q naught on it. I can throw the switch this way, and now I can say I have a current in the circuit, right? And so the current is just equal to dq dt, where Q is the charge on the capacitor. As charge leaves the capacitor, the rate at which it leaves, dq dt is just the current in my circuit. The only correction I have to make to that is that there's really a minus sign in here, because Q is the charge on the capacitor, and the charge on the capacitor has to be decreasing for there to be current. So when there's a positive current, the charge on the capacitor is decreasing, and so that's what that minus sign is. Now I can just use Kirchhoff's rules around this little loop. Maybe I'll put a little C here for the charge on the capacitor, and I'll say, so if I go the voltage around here, I'll say the voltage on the capacitor minus I times R is equal to 0. That is to say, if I use Kirchhoff's rule from, say, this point, I jump up the voltage on the capacitor. Since that's negative and that's positive, I go up by VC. That's the voltage on the capacitor at any given time. Initially, it's just the voltage on the battery when it's fully charged. But as soon as charge starts leaving, I'm going to call it VC. It's whatever's left on the capacitor, right? Whatever voltage is left, decreasing as the charge runs off. And then it's minus I times R, because I'm going in the direction of the current, and then I'm back to where I started from, equals 0. So, so here's an equation that sort of tells me how charge moves in this circuit, and I have to be if I'm a little careful here, I can sort of understand what's going on. I can say, look, the voltage on the capacitor is just the charge on the capacitor divided by the capacitance, right? Q equals CV, so V equals Q over C. And I'm putting a little C there just to indicate that it's at some intermediate time, that's the charge on the capacitor. And then it's equals I times R, but that's really just equal to minus dq on the capacitor over dt times R. And so if you look at these two pieces, I get QC over the capacitance is equal to minus dq on the capacitor dt times R. So this is a differential equation. It's an equation with a derivative in it. Generally, the easiest way to solve a differential equation is to separate the variables that you have. So in this case, I would want all the QC's on one side and all the T's on the other side, and then you can do whatever you want with the constants. You can't always solve a differential equation that way. Sometimes they're too algebraically complicated. But if you can, the first thing to try is to separate variables. Really, there are just two variables in this problem, QC and the time. And so if I was going to separate, I would write this as dQC over Q. Sorry, let me try that again. That's to say, if I multiply this side by dt and divide it by R, so I move the R to this side and the dt to that side and the QC to this side, I get this equation if I move the minus sign over. You can do that algebra on your own. That's not a lowercase c, that's not a subscript c, that's like that, right? And so this gives me the Q dependence in terms of time, right? And so I can just integrate this thing. I can say, look, if I integrate from when I started the thing to the end, I can say this is the integral from Q naught, or the charge I started with, to some later I'll call Q prime, or just Q maybe. Right? And so if I integrate both sides, this becomes log of QC, evaluated from Q naught to Q, equals T minus T over RC, because that just integrates to T. So this becomes the log of Q over Q naught is equal to minus T over RC. Well, I can raise e to both sides, right? I can put e to this side equals e to that side, and that gives me Q over Q naught is equal to e to the minus T over RC, or Q is equal to Q naught e to the minus T over RC. And so that's a charge at any time is equal to the initial charge times an exponential function e to the minus T over RC, right? This exponent, when t equals 0, e to the 0 is 1, and so what this graph looks like is that, right? Q, so if this is Q, this point here is Q naught, and this is time, and it tails off this way. And if R and C are really small, it'll this exponent will be really large, and this thing will tail off really quickly. If R and C are really large, that's the product of R and C is really large, this thing will tail off really slowly, and the charge will leak away really slow. And so how fast the charge runs off the capacitor through the resistor just depends on the capacitance of the capacitor and how big the resistor is. If the resistor is really big and the capacitance is really large, it'll take a very long time for the charge to run down. So the charge on the capacitor is Q is equal to Q naught e to the minus T over RC. And so at t equals 0, this is Q equals Q naught, or is CV, where V is the voltage on the capacitor, right? We could also say, we could say when t is equal to RC, whatever that value is, the product of the resistance and the capacitance, the charge on the capacitor has been reduced by a factor of E. This is about 0.36 times Q naught. .368. Just be clear. And so when t is equal to 2RC, Q is equal to Q naught over E squared. Which is about 0.135 or something like that. And so on. And so RC is called the time constant of the circuit. It comes out in units of time. And if you wait for an amount of time equal to RC, the charge left on the capacitor is about 35 or 40% of what it started out. If you wait for 2 time constants, the charge is down to about 13%, and so on. So this gives you some measure, RC gives you some measure of how long it's going to take that capacitor to discharge. again, V is equal to Q over C. And so you could say the same thing about the voltage on the capacitor. It will reduce at the same rate as the charge on the capacitor. You can also say, since the current through the resistor is equal to dq dt, or technically minus dq dt, but its magnitude, the magnitude of the current is just dq dt, right? And so that's equal to the time derivative of this guy, which is minus Q naught over RC e to the minus t over RC, right? It's just the time derivative of this guy, or the magnitude of that. And so, pause for a second. Q naught over C is just equal to V, the voltage on the battery, right? Q naught over C is just equal to V, and so the magnitude of the current in the capacitor has almost the same relationship. It's V over R times e to the minus t over RC, or you can call it I naught e to the minus t over RC. That is to say, the current at any time is equal to the initial current, which is V over R, times e to the minus t over RC. And so in each case, you can either talk about the current or the charge. It decays according to an exponential. Here's my current, here's my time, and this point where it crosses the current axis is equal to I naught.